Hello everybody, this is the notes for geometry class, section 6.4. What we are talking about is similarity. We've been talking mostly for chapter 6 about just proportions and ratios, scale factors. In the last section, 6.3, we talked about if objects are similar. And so the two things that we needed to have were corresponding angles, all of them had to be congruent, and corresponding sides had to have equal ratios. So all of the corresponding sides. So now, just like what we talked about with congruency, we started the same way. We said if two shapes are going to be congruent to each other, all the corresponding angles had to be congruent and all the corresponding sides had to be congruent. And then we talked about triangles. Well, with triangles, you only needed certain pieces of information. We had those 5 ways: side, 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 angle, side, angle, those things. If we had just that little bit of information, it was enough to say these two triangles have to be congruent to each other. And so we're going to do kind of the same thought process with similarity. With similarity, we need to have congruent angles, all of them, and corresponding sides have to have equal ratios. Well, with triangles, same idea. For them to be similar, you don't need all of those pieces of information. If you have just the right pieces of information, then the triangles will be similar to each other. All right, what we're looking at here is some given information. I have a 40-degree angle and a 60-degree angle up here at point A and around here at point B. Same thing, at point C I have a 40-degree angle, point D I have a 60-degree angle. So what I have are two pairs of congruent angles. Now, the 40-degree angle, it'll come up, the 60-degree angle will come up, and they're going to intersect at point E. Same thing down here. This, from point C, we're going to go up. Eventually, it's going to come up here to point F, and then at point D, it's going to come up here to point F to form a triangle. But the key thing is, you're given just two pairs of angles. With those two pairs of angles, we don't have anything about the length of that side in between. Doesn't really matter. All we have are those two angles. So when I click on the corresponding sides, what I get is that segment AE and segment CF. But notice right here. Here's the ratio of those two corresponding sides. Now, when I click on corresponding sides 2, it forms the other sides of the triangle, the third sides of the triangle. So we're looking at segment EB and segment FD. But again, notice the ratio of those two sides. Okay? We started with just a 40-degree angle and a 60-degree angle, and that formed a triangle. When you extended those sides up, it met at those two sides met at point E, those two sides met at point F to form the triangle. But notice these ratios are the same. And so different side lengths, but the ratios of those corresponding sides are still the same. Now, we had a couple months ago, we talked about this idea of a third angles theorem. If we have a 40-degree angle and a 60-degree angle, like we have at angles A and B, that's 100 degrees. That leaves angle E to be 80 degrees. Well, same thing at F. Because we got 40 and 60 at angles C and D, angle F has to be 80 degrees. So when we talk about similarity, all of the corresponding angles are congruent. We have that. And this ratio right here is the third side. It's side AB over side CD. Notice how all three pairs of corresponding sides have an equal ratio. It doesn't matter how big, how little the triangles are. We have corresponding sides. All three of them have an equal ratio. So these two triangles are similar to each other. But the key thing is we started with just two pairs of congruent angles, which leads to this postulate. It is called angle-angle similarity postulate, and the way we write it is similar to what we did with congruency. All we need is angle, angle, and we put the little tilde there. That means we're talking about similarity and not talking about congruence. But what this postulate says is, if you have two triangles, and in those two triangles there are two pairs of angles that are congruent to each other, like we had with the 40 degrees and the 60 degrees, it forces these two triangles to be similar to each other. Okay, so all we're looking for is just do I have two pairs of angles congruent in these two triangles? All right, so hit pause, try to answer these three questions. All right, what we're looking for again is two pairs of angles that are congruent in these two triangles. So in this first drawing here on the left, we have some given information. These two lines are parallel. That gives us a lot of stuff. Okay, what that gives us is corresponding angles. If we think of line LJ as a transversal, we have corresponding angles. And with parallel lines, corresponding angles are congruent to each other. We also have corresponding angles over here. Those two blue angles are congruent to each other. There's two pairs of angles. So triangle JKN, this top portion, will be similar to triangle, the whole thing, JLM. Those two triangles are similar because of angle-angle similarity. Now, we can use those two angles, but if you look at these two triangles, they're also sharing angle J. Angle J is the same thing in both of them. So we could have used any combination of two of those three. We have congruent, two pairs of congruent angles, we got similar triangles. Looking at the middle drawing here, again, we have our two triangles. So we're looking at the given information. We have an arc here and an arc here. There's one pair of congruent angles. Now, with this right angle here and this line segment, we got another right angle there. So there's two pairs of congruent angles. These two triangles are going to be similar because of angle-angle similarity. Now, a similarity statement. This is a similarity statement. What we want, triangle MNQ, that is similar to triangle, corresponding order matters. Okay, M, we don't know anything about M. You know, we have the other two pairs of angles congruent to another two pair, but M we don't know anything about. We don't know anything about angle O, so those are corresponding. Then I went to N, which is the right angle. So I'm going to go to the right angle in the other triangle, which is also N. And then up to Q, MN to Q, that's the angle with the arc in it. On the other triangle, that's angle P. So there's our similarity statement. All right, the last example here for this slide is question 8. We have one pair of angles, angle B and angle D, that are congruent. But we also got vertical angles. So there's two pairs of angles. All right, one quick application of this is recognizing, do you have similar triangles? And if you do, then you have proportions. Corresponding sides will have equal ratios, which gives you a proportion to solve. And that's what we want to do with this problem. So hit pause, try this on your own, then come back and see if you got the right answer. All right, it says, you can measure the width of a lake using a surveying technique as shown in the diagram. So basically what they did was, here's this lake, they put a point here at X, and then they measured certain distances. From point Z, they measured a 6 meters. To this point, they measured 8 meters. Over on the other side, measured from W to V, it was 104 meters. But notice that those two sides are parallel to each other. So the question is, what postulate or theorem can you use to show that the triangles are similar? Because of these parallel lines, what we have are alternate interior angles. This angle Z, I know it's kind of hard to see with this picture in here, but you have angle Z and angle W, alternate interior angles, because the lines are parallel. Those angles are congruent. And we also have the easier one, we got vertical angles. So this angle here at X and this angle here over the water also at vertex X. Those two angles are congruent. So angle-angle similarity is the reason these two triangles are similar. It says find the width of the lake, WX. All right, so what we're looking at. Sometimes it's helpful to have the triangle names written out so it helps you see the corresponding parts. Sometimes it's not necessary, but sometimes it is helpful. So what we're looking at here is triangle ZXY. Similar to triangle. Okay, Z was the angle that we talked about with the alternate interior angle. That goes with W. We went to X, which was that center point, so that's the vertical angle, so that will correspond to itself at X. Then we went to Y, which goes to V. So, because these two triangles are similar, we have equal ratios for corresponding sides. We are looking for the width of the lake. So I'll just call that A. It corresponds to, that is side WX, it corresponds to side ZX, which is 6. Again, because triangles are similar, equal ratios for corresponding sides. I went with A, which is from the larger triangle going across the lake. The only other thing we know is that segment VW, which is 104. Again, larger triangle, I'm putting in the numerator here. So that side corresponds to, it's the parallel side, it's got to go with ZY, which is 8. There is our equal proportions. And so now we can just cross multiply or just multiply both sides by 6. So 624 divided by 8, whatever that is. I have no idea what it is, so that's our answer. That's in meters. That's how wide this lake is. Part C says if xy is 10, find Vx. We would do the same thing. We have our corresponding sides of 104 compared to 8. If xy is 10, that's from the smaller triangle, what is Vx? So we could just set up that proportion, cross multiply, and solve. All right, that is it for these notes. Have a good night.